The Cambrian Explosion is the geologically rapid appearance of most of the major groups of animals in the fossil record around the base of the Cambrian. It's been a major headache since the days of Darwin, but since then we have a vast amount more information. We have multiple new lines of evidence that are shedding light on what was going on. That said, there are still a lot of outstanding issues, and today I want to give you an overview into what we know about the Cambrian explosion, what we don't know, and what it all means, as far as we can tell. First thing to say is that this video is going to be an overview. I'm not going to go into all the fine details of particular species and particular fossils, because that will come in future videos. What I want to do here is provide a baseline, a sort of primer, in what we know about the Cambrian explosion and the various lines of evidence that we have for it. So, this is particularly important because, amazingly, there are quite a few academics following this channel in various fields, and there are also people who have very little background in the subject at all. And everyone is equally welcome, and this is to make sure that we're all on more or less the same page in terms of what we know as a baseline. Okay, I'm guessing that this will be quite a long one, so get yourself a cuppa and settle in. I'm going to start with a quote from Darwin, because even in the 1850s there was the recognition that there was an interesting problem here. So he wrote in The Origin of Species, "As to why we do not find rich fossiliferous deposits belonging to these assumed earliest periods before the Cambrian system, I can give no satisfactory answer. The case at present must remain inexplicable, and may be truly urged as a valid argument against the views here entertained." I wish they wrote like that nowadays. But what Darwin was seeing here was the appearance of things like trilobites and brachiopods, all sorts of fossils in the Cambrian rocks, which had nothing as a precursor. There was nothing in the Precambrian rocks which showed any sign of an organic origin. There were one or two weird things which have been debated, well, forevermore, but mostly those turned out to be inorganic structures. And there was nothing as a precursor to the diverse range of complex animal life that suddenly appears in the Cambrian. There are multiple possible answers to that fundamentally. Firstly, we have the possibility that animals spontaneously diversified at this time, that they appeared and evolved very rapidly into all these different lineages, and it is a genuine evolutionary explosion. Alternatively, it could be something related to taphonomy, of how fossils are preserved, because the things that appear in the fossil record generally have hard shells. Could it be an explosion of fossilizable organisms, that they all had their ancestors going a long, long way back, but they didn't have any hard skeletons that could be preserved? Also, there's the option of, could they just have been somewhere else? Could life have been evolving in a place where we don't have the rocks preserved, and therefore we just don't see it? So there are various possible ways that you might look to explain this detail, and the most important thing to do, of course, is to find more fossils. Just for a moment, though, I want to appreciate what Darwin and his colleagues in the 1850s were working with. So this is a bit of Cambrian mudstone from North Wales, which has some complete fossil trilobites on it. They're rather lovely. It's a very standard sort of bit of slate from that sort of age, and you can see that the rock itself is ridged and wrinkled and buckled. This is an old rock. It's been through a lot. It's about 500 million years old, and in that time there have been mountain ranges going up and down, there have been continental collisions. The older the rocks are, the more they've struggled with life. And when you get back even further into the Precambrian, it's very hard to find rocks that are undeformed, that are not seriously affected by collisions with other continents, for example, and crumpled into mountain ranges and cooked. So the older the rocks are, the less chance we have of finding good fossils. So that's one aspect. And what they were working with was basically gentlemen, largely, going out with hammers into the hills and breaking open rocks until they found something that was clearly recognisable and obvious on the surface. So things like trilobites, like brachiopods, and so on. And this was the approach that was traditional and is still used by a lot of us today. But it is the fundamental approach, and it's limited. Because what you see when you split open lumps of slate and look for things in the sunlight is quite large fossils. Quite large, often three-dimensional fossils. At that time there was no real understanding of soft-bodied fossils, for example, stains on rock made of carbon films. They didn't really appreciate the significance of little blobs and things, and if they weren't immediately recognisable, they were often overlooked. So that explains to some extent why the record was so limited back in the 1850s. Today, the oldest trilobites we have are about 521 million years old. So this is not the earliest part of the Cambrian, which goes back to 538.8, but it's still fairly early. And below that, we don't see trilobites. There are a few little shelly bits and pieces and so on. But that's really the start of the clear animal fossil record. And that's what Darwin would have seen as the origin of animal life within the rocks. Since then, we've developed multiple new techniques. The next groups to look at are what are called small shelly fossils. When you dissolve limestones in acetic acid or hydrochloric or something like that, then you quite often get fossils falling out of them. The fossils can't normally be made of calcium carbonate, which is the most common shelly material, because they would also dissolve. But anything made of opal, silica, like sponge spicules, for example, or anything made of calcium phosphate, are generally immune to being dissolved, and you can just pick those out of the residue that's left. This is fine, and for most of the record that limits you to a relatively small number of groups. But in the early Cambrian especially, it seems that there was a very common process of fossilization which involved things made of calcium carbonate being partly coated or replaced by calcium phosphate. This appears to have been a quirk of seawater chemistry at the time, that it was just a very common process. And so you can dissolve limestones and get phosphatized fossils of things that would normally be dissolved. So things that were originally calcium carbonate, aragonite or calcite shells, bits of skeletons and so on. Even bits of organic skeletons have been phosphatized in this way. And this gives us what we call the small shelly fossils. It's a very imaginative name, I know, but you know, we're paleontologists, we've got to use our imagination where we can. And what this provides us with is an extraordinarily rich fossil record of small, up to a few millimetre, fossils from the early Cambrian backwards into the very latest Precambrian. The fossils do change through this interval as well. So the later ones include bits of the sclerites of things like chancelloriids. Got a video on those if you're interested. And things like mollusks, so things which are obviously little coiled shells. And they're relatively familiar in most cases. There are lots of little sclerites and things that we're not quite sure what to do with, tomotiids and so on, which are starting to become clearer. But then as you go further and further back, a lot of the most familiar ones start to disappear. And when you get down to the base of the Cambrian, you're really left with not much more than strange little tubes, sometimes with weird symmetry, things like anabaritids and cloudinids and so on. And these are an array of little tubular organisms that are often assumed to be related to cnidarians, so things like jellyfish, sea anemones, that sort of thing. Some of those make tubes, but a lot of them are very ambiguous as to exactly what they are. But it's only once you get into the Cambrian and higher up that we see things that we can say, right, that is definitely a mollusk, or that's an arthropod, or whatever it is. So yeah, it's quite interesting. The small shelly faunas appear to give us a window showing the origination of the modern groups of animals as we can recognise them around the base and the very earliest parts of the Cambrian. Of course, it may be that they went further back, but they weren't being fossilised. Maybe that window of phosphatization just wasn't as effective further back, or maybe the animals weren't living in the place where that window happened. But from what we can see from the small shelly faunas, we get the diversification of the major animal groups, again around the base of the Cambrian, slightly earlier than we see it from traditional paleontology. The next big new line of evidence that we can look at are the Burgess Shale-type faunas. These are slightly later. They are mostly late early Cambrian going into the middle Cambrian, and now there are a few even in the Ordovician, and one or two in the Ediacaran, but we'll get back to them. So these Burgess Shale-type faunas were revelatory in many ways. Before, we were stuck with shelly fossils, things with a hard skeleton that have a good fossil record that we can trace back to their beginnings effectively. But the Burgess Shale-type faunas preserved pretty much everything. For this, we are talking about places like the Burgess Shale itself, Chengjiang, Xinjiang, Sirius Passet, Sinsk biota. There are many, many of them now, about 50 all told, of varying degrees of quality. So the best ones, like the Burgess and Chengjiang, actually seem to preserve pretty much everything that was alive on the seafloor bigger than about 1 millimetre. And quite a few things that were floating around or swimming as well. So it's pretty impressive. And this is independent of what they were made of. So soft-bodied animals, completely soft labile tissues, not even with a cuticle, they're all fossilised. And what this has done is pushed back the fossil record of many major groups of animals way, way back into the early and middle Cambrian. Especially Chengjiang, which has been studied intensively across several provinces in China by large teams of people. And as a result, we have almost every phylum of animals is now known from the Cambrian, which is extraordinary. There are a few exceptions, some tiny microscopic animal lineages or ones that basically have no chance of fossilising at all. And bryozoans, which still seem to occur in the Ordovician only. But yeah, we'll get onto them again one day. But almost all of the major groups of animals are there in the Cambrian. Even more than that, though, in more recent years, in the last decade or two, we're starting to find that alongside representatives of a phylum, which are recognisably, say, an annelid, we are now getting things which are recognisably within a subgroup in that phylum. Particularly things like living families. There are multiple examples of this, and between these and the Ordovician faunas, we're now pushing back a lot of the living families to very, very deep in the Paleozoic, in the Ordovician and Cambrian periods. What this is doing is pushing back not only the diversification of the major groups of the phyla of animals back to the Cambrian, it's also pushing back the later stages of the diversification, the little branches of the tree. Those are being pushed further and further back, and it's all being crammed into the Cambrian or before. So it's an extremely important part of the puzzle. And its implications when you start looking at this and trying to quantify what that means for the origins of animal life are quite interesting. So far that's a sort of a one-way push down towards the base of the Cambrian and earlier. But in fact, Burgess Shale-type preservation is not restricted to the Cambrian, or even Cambrian and Ordovician. Because when you think about what the preservation actually is, we're looking at carbon films in mudstones. Things which are soft-bodied, that should rot away, that have been preserved. There are other characteristics as well, so the type of environment they tend to be in, but it's open marine, normally around the depth that waves can get to in storms, where you go from an aerobic area to an anoxic area. Things are being swept in, downslope, and that's the environment they've been preserved in as carbon films mainly. And we get that in the Ediacaran quite a bit. There are lots of deposits, mainly in China and the surrounding areas. So you have places like the Miaohe biota, the Lanqian, the Zunat, and most recently of all, the Tongshan biota, which is really interesting because it's in the very late Ediacaran. Most of them are deeper in the Ediacaran, so middle to early, but there are now ones like the Tongshan, which are starting to turn up in the latest part, where we should, according to all expectation you would imagine, find animals. And we are finding various typical Ediacaran things, but so far, even in the Tongshan, there are no recognisable animals in the same way that you get in the Burgess Shale-type faunas in the Cambrian. There are some tubes which are probably Cnidarian, but there's nothing that looks like any sort of advanced animal. There are no worms, there are no arthropods, there are no echinoderms, there are no chordates, there are not even any sponges. And this is apparently a general pattern. Some might argue that we've been unlucky, that all of these Ediacaran ones are simply sampling the wrong bit of the seafloor, that we're just not getting animals there, that maybe it was too anoxic. But they all represent algal floras, cyanobacterial remains and things like that, which we also get in the Cambrian deposits. So it looks as though, from what is preserved, they are directly comparable with what we see in these Cambrian biotas. Which makes you wonder, why are we not getting the animal component in anything in the Ediacaran, when the preservation looks to be the same, the environment looks to be the same, and the things that are preserved are mostly the same as in the Cambrian? Before we get into molecular clocks, I just want to cover a couple of definitions and address the question of what do we actually mean by an animal. Because people have a sort of intuitive understanding of what an animal is. It sort of mostly moves and it's complex and it's multicellular and so on. But it depends on exactly how you define it as to what we're talking about. So for this we need the concept of stem groups and crown groups. This is a standard in biology and paleontology now, but it might be totally unfamiliar to anyone else. So the crown group of a particular group, say animals in this case, is a chunk of the tree of life which includes all of the living members of that group, their last common ancestor going back as far back as you have to go, and all of the descendants. So whether those are extinct or not, it's that chunk of the tree that goes back to the last common ancestor of all of the living members of the group. That is the crown group. Then you have a branch that leads up to that point. So anything which is entirely extinct, which is more primitive, in inverted commas, than anything in the crown group, is what we call the stem group. And the stem group goes between the last common ancestor of the crown group and the next branch down with the next nearest living relative. So in the case of animals, that will be choanoflagellates. These are single-celled protists which have certain animal-like characters, and they have a quite distant ancestral branch with animals. Okay, simple enough. But that means that if we're talking about animals, if we mean the crown group, then we clearly have a multicellular, fairly complex organism. If we mean the stem group, that can actually be unicellular. You go far enough back and you get to single-celled ancestors. If you mean some sort of colloquial term of something big and complicated, being an animal but something else not, then you run into problems if, for example, there is a member of the stem group that evolved to be multicellular independently of animals. This leads to all sorts of confusion and complexity. So because we don't know what was going on in the stem group of animals, for the most part, we don't know quite how to apply these terms. We don't know what we mean when we're referring to an animal in some sort of loose, generic sense without defining it. So this is important. And when we're talking about something like an Ediacaran fossil being an animal, we need to actually say what we mean by animal. Okay, enough of that, but we'll be using that terminology just to understand what we're talking about as we come back to it through the rest of the talk. Right, on to molecular clocks. Molecular clocks are an extremely sophisticated and technical area of biology and paleontology that I am nothing like an expert in at all. So all I can give you with this is the basics. I'm totally aware that I do not understand a lot of the fine detail that goes into these models. So molecular clocks are a way of taking an evolutionary tree that has been generated by looking at the genetics of a wide range of living organisms, and then calibrating that tree backwards in time using fossil occurrences of the groups that are represented within it. You can then extrapolate, once you've got enough data, to look at the branch points within the tree that you don't have calibration points for. So take, for example, mollusks. Something relatively straightforward because a lot of things have shells. And we have a wide diversity of living forms. You can take the genetics, or a section of the genetics, of a large number of different groups of mollusks, different species, compare them via computer, and it will generate a tree for the most likely evolutionary history for these groups. Even the word most likely is a minefield, because there are all sorts of different approaches that are parsimony versus likelihood, and yeah, it gets complicated. Anyway, you get the basic idea. And this tree will be generated as the one that is most favoured by the data. And the branching points between two closely related species will be much higher up the tree than those which are more distant. So two species within the same genus might have branched within the last few million years, and we might have fossils of those going back 1 million years. And so you have a calibration point that this branching point cannot have happened after the date of this fossil. You then populate your tree with lots of these calibration points, and what you get is an assessment of the average or the range of evolutionary rates that have led to that number of mutations by which the genetics are separated, going back in time. So that's all fine, and you can get a whole set of data which is mutually self-consistent, that the rates are all relatively consistent within the tree, and that gives you a nice solid basis. But what you can then do is look for the deeper branches where we don't have any fossils. You can push that back and extrapolate that range of evolutionary rates of increases in number of mutations over time at the rate seen by the calibrated clock to push back to get an estimate of the deepest points on the tree, or invisible ones within the tree where we have no fossils. And this has been done to a very great extent now for animals, trying to clarify when the major divisions within animals actually happened and see how far back they go. The results have been, in general, shall we say, interesting, because there's been a huge range in the dates that have been estimated for the last common ancestor of all animals, which includes sponges and ctenophores and all of the very early branching ones. But the base of the crown group of animals is what we're looking at here. So when you do that, you get a range of data going back, in some cases, to virtually 1 billion years for that point, the base of the animal crown group. However, the results you get do vary enormously depending on the exact techniques you use, on which bits of the genetics you're comparing in the first place, what calibration points you use. And there has been, I think, a general trend in recent years for these dates to move gradually further upwards, closer and closer to the base of the Cambrian. Still, in general, I think it's fair to say that the normal sort of range of dates for the base of animals is somewhere around the Cryogenian, so before the Ediacaran, something like 600–700 million years. For the diversification of the other animal phyla, so things like arthropods and annelids and the familiar things today, those dates tend to be within the Ediacaran. Not right at the very end either, sort of within the early to middle part of the Ediacaran is fairly standard, but like I say, there is a lot of a range. But this is the the consensus sort of ballpark figure, if you like, for where the molecular clocks put animal evolution. This is a problem because it basically reinforces that worry that Darwin had when he saw the diversification of these major groups of fossils in the Cambrian and thought intuitively that this means that there must have been a long prehistory which was invisible. And the molecular clocks seem to be confirming that pattern, that we have a need for there to have been tens of millions of years of animal evolution, bilaterian evolution even, so relatively advanced animals in the Ediacaran before we find the fossils of them. So we're going to need some more techniques because something is obviously not giving us the whole story here. The biggest and probably most controversial revelation about this time interval is the discovery of the Ediacaran biota. These are an array of fossils now found from dozens of sites around the world during the Ediacaran. And they range from quite early, mistaken point goes back to 570 odd million years, right through to the end of the Ediacaran, possibly going into the Cambrian in Namibia. And they range from very shallow water to very deep water, and the diversity of organisms preserved in these deposits is remarkable. However, they are incredibly contentious. So most of them have a body form and a structure and architecture that is not closely similar to any modern animals, or even to our views of what the earliest members of those lineages of those animals should be. They don't obviously fit into even the early part of animal evolution. And yet, this is what we've got. There are strange frond-like creatures, there are sort of mobile mats that seem to digest the algal mats that they're sort of sitting on top of, and then move on and digest some more. There are helical sort of structures, spirally symmetric little creatures, sometimes threefold, eightfold. There are bag-like things, there are sacs with holes in the side. They are all anomalies. The more we learn about them, and we are learning quite a lot about things like reproductive patterns and so on, the more they just seem to defy easy explanation. And Dolf Seilacher, famously, is a very prominent paleontologist in the last century, proposed that these should be regarded as a separate kingdom of life, the Vendobionta, he called them. And there are still arguments in favour of that, that one could argue that these were a separate derivation of multicellular life from a unicellular ancestor, maybe in the stem group of animals, but maybe not closely related to us. The problem is that there are also within this biota things that do look much more familiar. So there is, in the Charnwood forest beds in England, Aurora lumina, which looks, at least at first glance, like a cnidarian. It was described as a cnidarian, and not only a relative of jellyfish and so on, but a crown group cnidarian. And this goes back something like 570 million years. It's a very old deposit. There are also real oddballs, like Kimberella is the classic one. This looks superficially like a bilaterian, with a nozzle coming out the end with spikes on that it seems to have used to scratch the algal mats it was living on top of, in a way that is at least superficially reminiscent of mollusks. But this has been argued that it is related to mollusks, or at least, if not mollusks, then bilaterians, maybe ancestral bilaterians. But there is no certainty. And all of these really important ones we will come back to and discuss in more detail. But for today, it's really trying to get an assessment of the Ediacaran biota as a whole. They are very strange organisms, and they are almost entirely limited to the Ediacaran. There are, however, now an increasing number of apparent holdovers turning up in the Cambrian, including some of the classic things like the fronds that we get, Chania and so on. There are things in the Burgess Shale-type faunas now that preserve things that appear to be very similar, frond-like organisms, and may actually be surviving ediacarans in the middle of the Cambrian. Part of the reason the ediacaran biota is so difficult to interpret is that most of it is preserved in a pretty much unique way. So this is a feature of the ediacaran seafloor, that it was covered in microbial mats. And what we have as the dominant type of preservation for the ediacaran biota is a strange array of death mask type scenarios, where these things die on the seafloor, are covered over by bacterial mats which mould them. And then various things happen, including sometimes the organism decaying and then sediment being pushed up into the mould to fill it from underneath. You get these odd sort of negative relief fossils. And what we have is normally in sandstone, so it tends to be quite coarse material that doesn't show very fine details. It doesn't show any internal structures or organs, and it just makes it very difficult to interpret these things. So ask 5 paleontologists what these things are and you'll get 7 different answers. And it may well be that they are not all the same group of organisms. On the other hand, it may be that most of them are. They are ambiguous. And we will doubtless be coming back to these again and again in future videos. But any time that we get ediacarans preserved in a different style, like the Tongshan biota, which I recently did a little video on, tends to be quite exciting because it shows us a different window into what life was doing in the ediacaran, and potentially helps us understand what these things were, and also what wasn't being fossilized normally, but might be under different circumstances. So we can't have these on our diagram as animals, so I'm not shading them in red, but they're also not plants or algae, so I'm not shading them in green. I'm going to call these ambiguous. They're they're shaded in as orange, and we'll just leave them there for the moment because we don't know whether these are crown group animals or whether they're stem group animals, or possibly even more distantly related to animals. And at the moment we have no way of getting a definite answer. A lot of people have opinions, and yeah, but nobody actually knows. Okay, we need something more definite. We've had the small shelly fossils, but what about the small carbonaceous fossils? This is a relatively new technique that was pioneered by Nick Butterfield and his students over the years, and has generated a whole new array of data. In this case, you take mudstones and dissolve them in hydrofluoric acid very, very carefully, and pick out bits of organic material, which are the remnants of soft-bodied, or at least cuticularized, so slightly tougher organisms that don't have a hard skeleton. It's a totally separate type of fossil record from the small shelly fossils, or from the Burgess Shale type preservation, or from anything else really. It's its own unique technique. One of the beauties of this technique is that you get these little fragments of organic material in aerobic environments, where there is decay, where the animals as a whole are broken down, and what you're left with are pieces of the animal or molt fragments. And then you end up with these exquisitely, beautifully preserved, really finely detailed fossils, usually less than a millimetre, quite often a lot less than a millimetre. And yet they are diagnostic because they have so much detail preserved in them. People have been working on these on Cambrian rocks, and this is now starting to be extended. So I have a video on some Middle Ordovician ones, the Osterberg biota, which is really exciting. But there has been an attempt to extend this back into the ediacaran as well. And what do we find when we look at this? Rather oddly, what we find matches the body fossil record, not including ediacarans. because you get really obvious animal remains, so things like the scalids of priapulid worm, or the little sclerites of wiwaxiids, or pieces of filter feeding apparatus and jaws of arthropods in the early Cambrian, going back into the fairly early Cambrian. But once you get to the very earliest Cambrian, there's almost nothing left. What you get there instead is algal remains, bacterial filaments, things like that. Problematic things that there's no indication that they have animal relationships. All of the diagnostic groups of animal material seem to disappear as you go back to the base of the Cambrian and into the Ediacaran. As far as I'm aware, I think there is a single scalid has been found, possibly representing a priapulid in the latest Ediacaran, or priapulid-like animal, one of these worms with little spikes, but it's not certain enough that that's what it came from. And what does this all mean? Well, this technique relies on the organisms in question having some remains that are tough enough to survive to this point and yield recognisable fossils, because completely soft-bodied organisms are not going to be preserved in this way. However, it does mean that although we can't say anything about the really earliest ancestors of many of the major subdivisions of animals, so the first bilaterians or anything like that, we wouldn't expect to be seeing in this technique. What it does tell us is that we apparently don't have widespread occurrence of more recognisable ecdysozoans, for example, these molting animals like arthropods and worms that have a cuticle that can be shed and that would preserve as these fossils. So it looks like perhaps at least the ecdysozoa and the sclerite-bearing mollusks, things like that, these early lophotrochozoans, all of these things appear to have originated genuinely, based on this information, somewhere around the base of the Cambrian. But it's not the only line of evidence we can look at, because so far we've just looked at the body fossils themselves. What about the trace fossils? Trace fossils are actually very important in this story, partly because the base of the Cambrian is defined at Fortune Head in Newfoundland at the first appearance of a trace fossil called Treptichnus pedum, which is the first complex trace fossil, or was, to appear in the fossil record. So this is a quite distinctive trace which sort of involves sort of loopy bits going off to the side and then going off on the side of that one. And this is believed to represent something close to a priapulid worm, because today priapulids make very similar traces. So we are defining the base of the Cambrian on the first appearance of a fossil that looks like it was a trail or burrow made by a priapulid worm. Of course, we don't know what the maker of this particular trace fossil was, and it may have been a more ancestral worm. It may conceivably have been something else entirely, which happens to have created the same trace. That's the problem with trace fossils. Unless you actually have the animal preserved inside it, you can't be 100% sure that that's what it is. But it looks quite plausible that this was something like a priapulid, an ecdysozoan worm, which is quite cool. It also matches really neatly with the only real animal SCFs, the small carbonaceous fossils from below the Cambrian boundary, being extremely rare scalids, which are the spines of priapulid worms, or their allies. So it looks like, from multiple lines of evidence, at the base of the Cambrian, there was something which was vaguely like a priapulid worm. I'm actually pretty happy with that. It looks fairly watertight. Okay, but how far back do these complex traces go? Well, this is where it gets difficult, because there are certainly numerous burrows within the Ediacaran rocks, and sometimes they're up to a centimetre or so wide. They're quite big structures. They're usually very simple, sinuous things, just underneath the surface of the mats, for example, but they don't preserve the animal or the organism that made them. There are some more complex ones have been described. For example, well, there was a video that I did just before this one, looking at something that purported to be a trail, a trackway made by something like an arthropod, maybe a lobopodian. But on close inspection, I don't think that holds up as an actual trail of anything. I think it's an artifact of the way that crystals grew around a little burrow, a very simple one like the rest of them. There are, however, other similar traces to Traptichnus that go back a little bit further into the Ediacaran, and it's possible that there were worms a bit like this that trace their ancestry a little further back. But we're not seeing trackways, we're not seeing anything that looks like it was made by a large, complex mobile animal with appendages. There are claims of these things. I don't find most of them to be at all convincing. So the one that I did recently was an example of why one shouldn't be too quick to believe some of the evidence for complex animals in the Ediacaran based on the trace fossil record, because each one can have multiple ways of being created. Okay, so from a trace fossil perspective, we can be pretty certain that there were genuine crown group animals by the end of the Ediacaran. How much further back do they go? That still remains uncertain, but certainly you can push it back a little bit further. But we don't see complex remains further into the Ediacaran, and it's worth remembering that not only animals move. There are, for example, protists, rhizarians, amoebae and so on that can leave trails and do leave trails today, and these can be up to a couple of centimetres wide. They can be quite large. There are also microbial things that can produce filamentous body fossils or branching networks that look like burrows. So we have to be very careful with saying that a burrow is definitively an animal, because quite often it isn't. And going back to the Ediacaran, imagine a phase before there were mobile predatory animals running around. You can imagine that protists had a field day. There may have been all sorts of variations that we simply don't have anymore because they were all too tasty. Remember also that cnidarians can move, and anemones, there are various types of those that burrow. We have a wide range of cnidarians that could potentially make trace fossils. Simple burrows do not necessarily mean advanced animals. So there's a lot of ambiguity left in the trace fossil record, but there's also at least some certainty that it gives us a timescale between the first things that were moving through the sediment and were of a decent size, centimetre or so, were sometime during the Ediacaran, and by the end of the Ediacaran you have things that were making complex traces that look like certain modern groups of crown group animals. So where did the crown group of animals originate, or what point in that sequence? We still don't know. But it gives us some constraints, which is always a good start. Okay, what else have we got? One other type of exceptional fossil preservation is what we call phosphatization of extremely small organisms, so Austin-type and Doshantos-type. And these are very similar. They only preserve things up to about 1 millimetre or so, and they occur at various points through the Cambrian and also in the Ediacaran. So the Austin-type preservation, which is mainly from the late Cambrian, but there are also some faunas in the early Cambrian, a Quanchuan pool biota for example, which preserve really beautifully detailed microscopic animals. And we do mean animals. In many cases they are larval animals. They are still sort of wrapped up into a ball, having not quite hatched out of an egg yet, but they are clearly recognisably animal. including scaly-dophilin worms, related to phaeopelids again. There are also cnidarians, olivoides, and things like that. There's a whole array of, not very diverse, but a reasonable diversity of definite animals in these Cambrian phospholites. In the Ediacaran, there are also sort of 580 to 600 million year old phospholites, which you can dissolve out these tiny microscopic, exceptionally preserved things from. And those, in that case, are embryos. They're all sort of balls of cells in different states of division. The problem is that as far as we can make out, they can all be explained as algae. There don't seem to be any there which are recognisably animal and have to be animal. Some are fairly complex, but those are more likely to be things like volvox, that sort of thing. So there are clear differences between these Ediacaran, but they're quite early Ediacaran phospholites, and the ones we get in the Cambrian. Again, it's not a great constraint because we don't have these deposits where we really want to see them in the latest Ediacaran, for example. But again, it's another constraint. By the time we get back to the early Ediacaran, it looks like there's nothing that we're seeing as animals. Another really interesting point for discussion is that I keep talking about these microbial mats that give us this Ediacaran preservation and all of the adaptations that things have to living on or burrowing underneath them. And those mats, these microbial biofilm surfaces that covered the sea floors through most of the Ediacaran, suddenly disappear as you cross into the Cambrian. You even get fragments of the mat's textures in the SCF floras in the earliest Cambrian, but they basically decline very rapidly as you cross the boundary into the Cambrian. Why is this important? Because if you had large numbers of mobile animals scurrying around eating things, you would think that those mats would be firstly disturbed and secondly eaten and basically lost. And this also suggests that you might have a major change in ecology around the end of the Cambrian with the rise of things that disturbed the mats. And there are yet more lines of evidence that you can dive into if you want to, with things like geochemistry, evidence for nutrient cycling through the ocean system, biomarkers, which are molecules that are thought to be diagnostic of particular groups of organisms. There's been a huge debate in the literature in the last 10 years or so about biomarkers that were meant to be from sponges, particularly demosponges, going back to the Cryogenian period. So really quite ancient deposits, 700 million years or so, diagnostic biomarkers from sponges. Problem is, they're probably not sponges. So there is now evidence that instead of sponges, rhizarians also produce these. These protists can make the same biomarker. And even worse, some very common biomarkers, or sterols, compounds produced by algae, can be modified during geological time and burial and transformation to a rock into these same biomarkers. So probably it looks like the biomarkers for sponges are ambiguous, but there are lots of other little details. So, for example, there were biomarkers taken from a Dickinsoniid, one of these Ediacaran biota classic organisms. And those were shown to contain, or shown that the Dickinsoniid contained large amounts of cholesterol, which today is a feature exclusively of animals. Now, cholesterol does exist in other organisms, and you can easily imagine a stem group organism which is not closely related to animals but is somewhere in the stem group also developing a higher proportion of cholesterol and that giving us that signal, but it's other lines of evidence that we can use. Okay, I think that's probably all the ones we need in order to get a bit of a feel for how the whole picture looks. So So here is the end result. A confusion of expectations of really deep origins based mainly on molecular clocks and also common sense ideas of how long it should take to get to the diversity we see in the Cambrian, conflicting with a very abrupt appearance in the fossil record of the major groups of animals, recognisable, definite animals in most cases, which appear to occur right at the very end of the Ediacaran going into the earliest Cambrian. And between the two, we have this whole area of ambiguity, the Ediacara biota, and various other bits and pieces as well. So these tubes, are they animals? Are they algae? Are they all cnidarians? There's a lot of uncertainty with these. But the normal assumption in recent years among paleontologists, I think it's fair to say, most commonly people are assuming that the Ediacara biota is actually an intervening step. It is showing us the earlier stages of animal evolution. Crown group animals, the divergences of the major lineages, so the bilaterians and so on, are all found within the Ediacara biota. I find this personally very difficult to accept because there are such radical differences in the body plans with the Ediacara biota and the major groups of animals that we're looking at. It's not easy to fit these in a sensible way that is seamlessly going from one major group to another via Dickinsonia or Charniates. It just doesn't make sense to me in a way that I would like it to. But if that's not the case, if we have a genuinely abrupt Cambrian explosion, then we need to find other ways to explain how we can get such a rapid diversification or separation of the major lineages and the appearance of the major body plans in such a short time. And for that we'd be looking at things like either internal genetic mechanisms that we don't fully understand yet, or we'd be looking at external forcing events. I mean, things as daft as nearby supernovae producing large amounts of cosmic rays that lead to an increase in genetic modification by mutations. It starts to get very sci-fi very quickly if you let it. But it is something that we have to get a handle on if we're going to explain it in a way that everyone is happy with, if we go down that route. So on the one hand, we've got a big problem of how the Cambrian explosion could be as rapid as it appears to be. And on the other, we've got a possible explanation with this Ediacara biota that may kind of fit into the gaps of all our missing parts of the tree, but you really have to squeeze them in to make them make any sort of sense. So on a personal level, I tend to think that in the last few decades especially, we've been too quick as a paleontological community to accept evidence for animals and specific groups of animals in the Ediacaran without enough scrutiny. Because sometimes it feels like the first hint of something that could fit into a certain gap is just sort of published in a high-impact paper, accepted by the media, and ta-da, we solved it. Except when you look at them more closely, as we saw with this potential Lobopodian burrow from the Shibantan formation in the previous video, it's not really that convincing at all. So what I see as the general pattern, and on a purely personal level without any scientific proof that this is the scenario that works best, is that you can understand everything we see in all these lines of evidence as a mutually consistent pattern showing an Ediacaran diversification of something which may well be stem group animals for the most part. There may be cnidarians. That's the one group that I think is reasonably good evidence suggesting that they were there in at least the late Ediacaran, maybe back into the middle. We'll look into more of those things in detail. But for most part, I think that the Ediacara biota is better kept as an extinct group of organisms that may have been an offshoot from the stem group of animals, rather than a crown group metazoan. Because everything else that we see, the SCFs, the small shelly fossils, the mats disappearing, everything that we have points to a very rapid transition from basically no animals to animals everywhere, diversifying into the major phyla and then into the subgroups, the orders, the families, very, very rapidly. So if I had to summarise my views on this, I think we should be spending more time looking at potential explanations of how we could get an extremely rapid diversification, an elevated rate of evolution at the base of animals, which would explain the patterns that we see. However, that is just a hunch. I do not have the answers. Nobody else does either. Lots of people have very interesting opinions on these things, and we don't know where the full story is going to go. But so far, I think that there has been too much emphasis and too much reliance on the molecular clock predictions, and not enough emphasis on looking at how the clocks can be broken, how particular phenomena that could apply to early animal evolution may give us a way that the clocks do not actually work when you're dealing with the origin of this major group in the history of life. But that is a sort of thing I couldn't publish in a scientific paper because it is purely my own speculation, and that's fine for YouTube because it allows me to get ideas out there for people to think about, say I'm a complete nutter, and then disregard anything else that I ever publish. But hopefully that won't happen, because this is the sort of place where we should be able to take a step back, look at where the evidence is pointing, where the balance of evidence goes, and start questioning our assumptions. Because that ultimately is what science is about. Being too dogmatic about we must have a deep origin of animals well back into the Ediacaran, and they must have diversified at 560, 570 million years ago, that's not scientific. That's an expectation based on what we think should be right, based on our current experience. So hopefully that's given you lots to think about, but it is, as I say, just the baseline. This is an introduction to why there are big problems still in interpreting the Cambrian explosion. You can go down one route and think you've solved it, but you still have other arguments pointing in a different direction to worry about as well. So have fun worrying about it, because it deserves a lot of worrying, and hopefully we'll be doing quite a lot more worrying over the coming years. Right, I will leave it there because I need a rest after all that. That's my longest video yet. Thank you very much for sticking it out to the end, and I look forward to seeing you again.